Okay, we are going to do some more polar coordinates stuff. Last time we just looked at what polar coordinates were, r's and thetas with respect to x's and y's. And we discovered that our ordered pair x and y satisfied the property that x squared plus y squared was r squared. X is r cosine theta, y is r sine theta, and the tangent of theta was y over x. We discovered that even though we knew that since probably birth. So,
Did you record it?
I did hit record. Polar coordinates were generated by rotating a ray through the polar plane. This is the pole. We take a ray and rotate it. As that ray rotates, it changes its length, r, and it forms an angle with the positive x-axis of theta if you rotate it that way. If you rotate it clockwise, then theta is a negative angle. And it passes through an ordered pair in our rectangular coordinates xy plane with the property that x squared plus y squared is r squared. X is r times the cosine of theta. Y is r times the sine of theta. And the tangent of angle theta is y divided by x. We also discovered the very basic graph in polar coordinates is a circle centered at the origin or a circle centered away from the origin. So in our list of some basic graphs, that r is equal to just some number, let me use the letter a, is a circle centered at the origin of radius a.
Thank you.
If I slap a cosine next to that a, it shifts the circle onto the x-axis, depending on whether a is positive or negative. If a is positive, it goes over here. So it's a circle with a diameter of a. And then if I do the same thing with a sine, it puts it up the y-axis if a is positive, on the negative y-axis if a is negative. And to convince you of that, I'll do one of these. For instance, if I have the equation r is equal to 6 sine of theta, and my instructions are to convert, how am I going to make a c out of that? Convert this equation to rectangular coordinates. Coordinates with 2 O's.
Yes.
Yeah, it sure looks funny, especially when you cram your letters all together. To convert that to rectangular coordinates, I'm looking right here. Here. Then if I had an r in front of that sine of theta, then I can just replace r sine theta with the letter y. So I'm going to take that equation given and multiply both sides by r. Okay. So multiply both sides by r. So this becomes r squared, and I'm going to put the r right here. And I have a conversion to rectangular coordinates for both the r squared and the r sine theta. R squared is x squared plus y squared. R sine theta is y. So now we go and convert I have that x squared plus y squared is r squared. And then r sine theta is y. And then from my experience, I know that to be the equation of a circle, but it's shifted away from the origin. I can find where it's been shifted by completing the square. So I'm going to move the 6y next to the y squared, leave a gap, and I'm going to add that constant to both sides of the equation. That makes y squared minus 6y plus that constant factors a perfect square. Okay, we can find it by thinking of a number that has two factors that add to 6, two identical factors that add to 6. Or if you want to do this mindlessly, it's always 1/2 this middle term, 1/2 the middle term squared. Half of 6 is 3, 3 squared is 9. So I add that to both sides, but now this does indeed factor. So I use the 3 from here and the minus sign from there. It factors as y minus 3 quantity squared. And now that's the general form of a circle with center of HK and radius of r squared. So my center here is 0, 3, and my radius is equal to 3. So that moved the circle's center up to here. That's the center. And it passes through. That's almost a perfect circle. That's pretty good. A little heavy down there, but that happens as you get older.
So in your picture, when we had r equals a sine theta, wouldn't it be up 0, a over 2? Because the diameter would be a?
Right, because that's the diameter. So you're right. So right, this is going to be 0a up here.
Oh, okay.
Right, that number in front is always the diameter of the circle. So here I've got a circle whose diameter is 6. Thank you for catching that. What does that look like? Off the screen. I'm on the screen, but it's awful faint. Darker markers. I still got a little bit of board left over here. What we're going to try to do is build a library of polar functions whose graphs we know with a minimum amount of effort, where we don't have to convert to rectangular coordinates. When we see the equation, we know it's a circle. If we see an equation, we know it's a cardioid. We see an equation, we know it's a rose curve, things like that. But in order to build this library of functions, we got to do the grunt work first, but that doesn't mean we have to reinvent the wheel each time. So today I'm going to sketch some of the other graphs by plotting points, which is a very painful way of graphing. You were to graph every single thing in rectangular coordinates by plotting points. What a waste of time when you know equations of lines and parabolas and hyperbolas and stuff like that already. You can just kind of quickly get a rough sketch. Okay, so circles are the first ones. R is equal to a number is a circle centered at the origin. R is equal to a number times a sine or cosine is a circle moved either. Sines always are going to be symmetric to the y-axis. Cosines are always going to be symmetric to the x-axis, even with our other graphs. So the next easier curve is something called a cardioid. Not quite a circle. Cardioid is shaped like a heart. And these cardioids are going to be shifted by taking something like this and adding or subtracting this number. So cardioids might look like this. I don't know how to spell it. Cardioids. I don't know, maybe something like that. Cardioids. I need another I.
I right before.
I-O-I.
Oh, yeah, yeah.
I think it's
I-O-I?
I don't know.
I-O-I.
Three
That's how I spelled
vowels.
it.
Cardioids. Cardioid. Cardioid is going to have one of these shapes, either that way or that way. That's going to be a cosine, or it's going to be that way or that way if it involves a sine. And so the general equation is going to have the r over here. That's going to play the role of the function. That's the f of theta. And now I write my function of theta over here. It's going to be an a plus or minus a times the cosine of theta, which gives you those guys. Cosines are symmetric to the x-axis. Or r is equal to a plus or minus a times the sine of theta. Has a common factor of a. And you're going to get a heart-shaped graph. And so let's look at a real basic one. Let's see if this marker works better. So I'm going to graph you this one. It's still blue. Let's see which one I have in the notes, because I'm going to post these notes on Blackboard. That one. And we're going to sketch a graph of r is equal to 1 plus the sine of theta. And I'm going to plot reference angles all the way around the unit circle, but I'm not going to plot those goofy ones that give me square root of 2's over 2 or square root of 3's over 2. How big is square root of 2 over 2? 0.7, right? Square root of 3 over 2 is, I don't know. So I don't want to plot those. I want to plot the values of theta that give me whole numbers or even halves. So for sines, I'm going to plot pi's over 6's, and then the quadrantial angle, 0, pi halves, pi, 3 pi halves. So I'm going to plot that all the way around the unit circle. Make a table of values. I'm make them horizontally so they fit.
The versatility behind that.
So I'm going to plot 0. I said the pi 6's. So pi 6 is next. And then I'm at pi halves. What's the second quadrant version of pi 6? 5 pi over 6. So the next quadrantial angle will be at pi. Now I need the third quadrant version of pi over 6. 7 pi over 6. Now I'm down there at the negative y-axis, which corresponds to 3 pi halves. Then I am at which pi 6?
9 pi over 6. Wait.
11, not quite 2 pi.
There we go.
Is 9 pi over 6, isn't that this one?
Yes, it is.
So we're at 11 pi over 6, and then we close it up at 2 pi. The 2 pi gets me back to here. Sine of 0, and sine of pi, and sine of 2 pi. What are those values? Those are all 0. So here and here, and if I were to plot a 2 pi, this is 0, so r is going to be 1. So r is 1 here and here. In which two quadrants is the sine positive? Top 2. So the sine of pi 6 and the sine of 5 pi 6 are the same value, and they're both a half. So this will add to 3 halves. So at pi 6 and at 5 pi 6, r is plotting a point out at a length of 3 halves. What's the sine of pi halves and 3 pi halves?
And
The other one? The sine of pi halves and the sine of 3 pi halves is 0, right? So
1.
this is going to add to 1, and that one is going to add to 1. So the two left are 7 pi over 6 and 11.
Sine of
Yeah.
0.
Right, sine of, good gosh.
Wait.
Sine of pi halves is
1.
1. So those add to 2.
Okay.
Can we erase that tape?
Edit it.
Sine of pi halves is 1. Sine of 3 pi halves is -1. That's what's going to put the little dimple in it. And it's going to be like that, right? I hate plotting points. I've gotten this graph 10 times faster. What are the values of the sine at 7 pi over 6 and 11 pi over 6? Negative 1/2. And so this is going to add to positive 1/2. Okay, and so now we're going to plot them. So I got to make some room to plot them. Let's do it right here. Then. Okay. Oh, that's a good one. That's 0, pi halves, pi, 3 pi halves. So now let's put the pi 6's in here. Pi 6 is going to be about, well, this pi halves is the same as 3 pi over 6. So it's going to be 1/3 of this sector. So it's going to be about right here. Keep that straight line going, and that'll give us our 7 pi over 6. And then our other pi over 6 is going to be about that distance up here. So there's my graph paper. That's 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi halves, 11 pi over 6. So imagine your graph paper is divided up. Those are the only ones I'm plotting, so that's all I need. So let's make that 1 unit. So when I plot 0, 1, I go out on an angle of theta is equal to 0 and plot the point right there. Right, so that's 1 unit. Our point goes right here. 0, 1. Right? Now, if that's 1 unit, 1.5 units is about that long. So there I am right there on top there. And now at pi halves, I'm 2 units long. So 1, 2. Okay, then at 5 pi over 6 here, I'm at 1.5 again. So that was 1.5. Let me duplicate that here. And at pi, I'm back to 1. So I've just plotted these. Oops, now I'm at, right, 7 pi over 6, I go to 1/2. So if that's 1, and that's about 1/2 right here. 3 pi halves brings me back to the pole. And then 11 pi over 6 is back at 1/2. So here's what's happening. We started here, it's tracing out an infinite number of points in between the ones that I've plotted, travels back to here, back out to there. If this were a minus sign, so this is with the plus sign in between, this is when I look at the minus sign, where the little peaky part of the heart is always at the pole, at the origin. Okay. Cosines look about the same way, except for they're going to be symmetric to the x-axis. And instead of plotting pi 6's, I would plot pi 3rds, right? Cosine of pi 3rds is 1/2. If I make these numbers different numbers, it has essentially that shape. If I change this to a different number than that one, depending on whether this is bigger than that one or smaller than that one, it looks like a cardioid with less of a dimple, or it looks like a cardioid but with a loop in it. So if you're graphing something like R is equal to A plus or minus B times the sine of theta, R is equal to A plus or minus b times the cosine of theta, you're gonna get something that almost looks like a cardioid, almost looks like a circle, but it's got a little teeny tiny dimple in it. Either that way or the other way or up and down, just like that, barely has a little dimple in it. Or it might have an exaggeration with a loop in it.
Is it possible to have a cardioid where the dimple is pointing diagonally?
Not with these forms.
Okay.
You'd have to do something else to it, right? In the polar plane, you'd have to do a rotation, which involves a complex number. So we don't have that.
So when we're graphing this, we are in the polar plane.
Correct. That's why I'm grabbing those dotted lines. Okay? So these things aren't called cardioids. They look almost like lima beans. Anybody cook with lima beans? And that's what they're called. They're called. But that C has a funny little thingy on it. It has a, let me see what it looks like in the book. Where am I? Where did they write this? They put a little gizmo under the C. I don't know what that gizmo is. Does anybody have a language in which they use gizmos under their C?
In French.
French?
Yeah.
It's
How do you say it?
Limason.
It's Limason.
Limason?
Limason.
I'm from Tennessee. That's a Lamacon where I come from. Did you get your Spanish thing straightened out? So it's the same problem. Let the French say it the way they want to.
The French are wrong about those things anyway.
Now, when it has a loop and when it doesn't have a loop, depends on this relationship here, and I never know, so I look it up. It has a loop if there's a minus sign and first term divided by this. Oh God, who can absolutely remember this? I can't possibly remember that. I don't know.
In French, that translates to cocoa.
It translates to what?
Oh, because it looks
Cochlea.
like the
Which is the little thing in your ear?
Mhm.
And why did they name that thing in your ear that? Does it mean that it looks like a coconut?
They named it out when we used to use the concert.
So I'm not gonna know when it has that or not. Okay, so those are cardioids. Let's see. It's got the little loop in it when first number divided by the second number is smaller than 1. So the loop occurs when first number divided by the second number is smaller than 1 and with a minus. Then it has a loop in it. Otherwise, it just has a little bulge. An innie, it has an innie. And I guess it tells us, I don't know what the B minus A is. It tells us something, I don't know, I just fake it. That's right. The ones that are fun to graph are the rose curves.
Is this the next type?
Yeah, because I don't want to graph those. So it'll be just doing that kind of stuff. A rose curve will have a multiple angle. Instead of just a 1 times theta here, it has a number times theta there. And the number in front of the angle is going to tell you how many little loops the rose is going to have. Right? A rose curve is going to be traced out something like that. And that would have 3 in front of the theta. Or we might get something like this. That would have a 2 in front of the theta. If there's an odd number in front of the theta, it produces that many petals. If there's an even number in front of the theta, it produces 2 times that many petals. So this would be a 3 times theta, and this would be a 2 times theta. So in general, R is equal to A times the sine of n theta, or R is equal to A times the cosine of n theta. produce rose curves. If your rose curve has a petal that is symmetric to what we know and love as the x-axis, then it's going to have a cosine in it. I should have said it the other way. A cosine of n times theta will always have a petal symmetric to the x-axis. Always. But the sine of n times theta will be a shift of it, 45 degrees. So the sine will be symmetric to the y-axis, but it'll have petals symmetric to the y-axis. But we'll see that by plotting points. So the next one I want to graph is going to be r is equal to the cosine of 3 times theta. We'll plot it by plotting points, graph it by plotting points, which takes a little bit of time. It's this 3 that's going to give me the petals. And to keep me from having to plot things like r is equal to square root of 3 over 2, or r is equal to square root of 2 over 2, I want to pick values so that 3 times theta is either 0, plus or minus 1, plus or minus 1/2. So where is the cosine? What angle is cosine going to be a half?
Pi over 3.
At the pi over 3's. So I'm going to plot values where 3 times theta is pi over 3. So I'm going to plot pi over 9's. Right? So that 3 times that pi over 9 would give me a pi over 3. So I'm going to make my table like this. I'm going to work backwards. I'm going to plot values of 3 theta. Then I'm going to divide by 3 to get theta. And then as I do that, I'm going to get r. So let's pick our 3 thetas first to be around the unit circle, the quadrantial angles, and the pi over 3's. But, okay, so let me do that. So I want to go 0, pi over 3. So notice I'm plotting in the middle row. And then I'm at pi halves, 2 pi over 3. Then I'm at pi. What's the next one? 4 pi over 3. Then I'm at 3 pi halves. And then I'm at 5 pi over 3. And then I'm at 2 pi. I'm going to put the 2 pi in here this time. Because what I did is I picked values of 3 times theta. Now I'm going to generate the first row of my table by dividing each of those by 3. So 0 divided by 3 gives me 0. Pi thirds divided by 3 gives me pi ninths. Pi halves divided by 3 gives me pi sixths. This gives me 2 pi ninths. And this will now be at pi thirds. Divide that by 3 and I have 4 pi ninths. Divide that by 3 and I'm at pi halves. Look how long it took me to get through the first quadrant. I've got 1, 2, 3, 4, 5, 6, 7. I lost count. I got 7 angles I need to plot just to get to a 90-degree angle, right? So if I divide this by 3, I have 5 pi over 9 and 2 pi thirds. So I haven't gone all the way around my unit circle yet. Think about when you graphed these kind of things in the XY plane. Y is equal to cosine of 3x. What does that 3 do to your cosine curve in the XY plane? Squishes it together, right? It changes the period. The period used to be 2 pi, now it's 2 pi over 3. 2 pi over 3, that's going to generate one of the loops of our rows, or at least get it started. So I might need more values, or maybe I could fake the rest. Let me make my table look prettier. There. Okay, now what I'm gonna do is, these are the actual numbers that I'm plotting, right? The 3 thetas. So I'm gonna compute R at each of those values. So I gotta take the cosine of the numbers in the middle column. So what's the cosine of 0? Let me do the quadrantial angles. What's the cosine of pi halves?
0.
Cosine of pi? Cosine of 3 pi halves? Cosine of 2 pi? Okay. And then the cosine at pi thirds is a positive 1/2. What about at 2 pi thirds? You guys remember how to plot a negative value of R?
Yeah.
Yes.
Okay. Cosine at 4 pi thirds, still negative 1/2, but now we're at 4th quadrant here, 5 pi thirds, positive 1/2. So now let me get my black marker again and let's get the polar grid set up here. So I'm graphing R against theta now. So we got to squeeze in those pi ninths kind of things. So let me see if I can do that kind of neatly. Okay, so there's my 0, my pi halves, and my pi, 3 pi halves. So to figure out how big pi ninths is, imagine the top half of the unit circle that goes to pi. If I cut that into 9 congruent slices, how am I gonna get 9 congruent slices out of this? I don't know.
Divide into thirds into thirds.
You divide my thirds into thirds,
Yes.
so put 3s here, and then cut those into thirds?
Yeah.
Holy croly. Okay, so let me kind of eyeball it. Do those look like thirds if you're looking at circles?
Yes.
That looks pretty good.
It looks pretty good. So the first one will be pi thirds, 2 pi thirds. Oh,
No, that's 4.
those are 6s.
Yeah.
Those are 6s. Pi 6, 2 pi 6, which is pi thirds, 3 pi 6 is pi halves, 4 pi 6 is 2 pi thirds, 5 pi 6, and pi.
So you need to get rid of the.
Bottom 2.
So I'm not gonna look at the other ones, right? I'm just gonna look at the thirds, and now I'm gonna cut these into thirds.
No,
that's
that would be.
the same.
Erase the bottom 2,
Well, you need the pi overs.
Oh, I see what you're saying. I just want the thirds. And
Yes.
so this one
Yes.
is pi thirds. Let's stretch that down here. And that's 1 pi thirds, that one. That's a 6. So in other words, this arc is congruent to that arc, is congruent to that arc. Well, I don't need those. That makes my hands nice and yucky. Now I gotta cut each of these into thirds. So maybe from there to there. Okay. That was good. I put this thing. Good shot.
No.
So this is a 9. Right? We don't need the 2 9ths, do we?
Yeah, we
do.
do.
1 9th, 2 9ths, 3 9ths is pi thirds. So that's 2 pi over 9. 3 pi over 9 is pi thirds. So let me draw these as straight lines through the origin. Gosh, here's where I'm gonna get all busy. Okay, that's gonna go here. Those are here. So I'm gonna connect this dot to that dot. Got a little bit wacky. I need 2 of them, so 1, 2. So I'm gonna connect this dot, to that dot. Kinda. That's where I hope I can fake the rest. Maybe. Right? So that's 1 9th, 2 9ths, 3 9ths, 4 9ths. Oh, I gotta go over here, don't I?
Yeah, that's not 4 9. You have to split that top one.
Okay, so I need to go about that big. Oops, I'm gonna have to go here. No, I don't know where that's going to go.
Okay, I think I see what to do.
Do you?
So, yeah, add that distance between pi ninths and the x-axis, and then like put it right to the left of pi over 3.
To the left of pi over 3.
Yeah,
Yeah, I know. Oh, there's gotta be one more here.
yeah.
Because that's 3/9, and that's,
That's not a.
4.5 then.
oh, son of a biscuit.
We did choose 3.
Okay, I know. I'm gonna fake it from here. If I need the other one, I'll put it in there. But I do, don't I? 1/9, 2/9, 3/9, I do need another one. I need another arc in here. Here.
Yeah.
Yeah.
2, 3, that's 4 pi over 9. Okay, I need it, right? Because I got a plot of 4 pi over 9. Okay. I threw my lid on the floor.
You did. I think it's right behind you, it's the white cap.
It is a white cap. I almost pulled something going down there to get that. What would you have done then? Okay, my first ordered pair is the ordered pair 0, 1. Here's 0, I gotta go out 1 unit, so let's make that 1 unit. Make it pretty big so we can see it. That's 1 unit. Already got one of those?
Yeah.
1 foot is 1 unit. Now at pi over 9, we put a half a unit. Okay, pi over 9 goes to a half, so that's 1, go to a half. Pi over 6 hits the origin. So pi over 6 is, shoot,
So
It's just
It's
halfway
right
between
here.
two, yeah.
pi over 6 is here. Goes back to the origin.
Yeah, it's just,
So look what's happened. Before I hit the 2 pi over 9, it went like that. Okay, so that's this. Now I'm at 2 pi over 9, this little black dotted line, and I have to plot a length of -1/2. How do you plot a negative on my 2 pi? I reflect it back down here. So which one does that go to? Good gosh, give me a ruler. Maybe this one? So it goes down to a half. So look, it went from here to here to a half. So that's this. At pi thirds, I'm at -1. So here's pi thirds. I gotta go down to negative, so here's pi thirds, go back to a -1. So it's gonna continue there and hit the tip of that pedal. So, and then at 4 pi ninths, I'm at -1/2. So 4 pi ninths is here, there's about a -1/2. At pi halves, I'm at 0. Okay? Then what? At pi halves, I'm at 0. Let's skip that one. Let's go to this one. That's the tip of the next pedal. At 2 pi thirds, I go to 1. 2 pi thirds. So that's 1 pi third. That one was 2 pi thirds?
Yeah.
So it's going to go from here back to 1. Then I guess we'd have to plot the rest. But
we don't have
you'll just
to.
believe me that it's gonna all be nice and symmetric, right? So it's gonna come back into here and go like that. Guess how far apart the tips of each of these petals are? Let's go in degrees. How many degrees in a whole circle?
360.
Divide that evenly into 3 equal petals. They're all 120 degrees apart. 120 degrees is how much in radians?
2 pi over 3.
2 pi over 3. So they're all 120 degrees or 2 pi over 3 apart. Cosine always has its first petal symmetric to the x-axis. So if you know how many petals you have, the giveaway is this number here. Odd number, it's that many petals. Even number, there's twice that many petals. So if you can find the first one, then divide your 360 by that many petals, you can get the tips of the other petals and get the picture all faked out. Okay? So let's look at a sine and let's look at an even number of petals. And after we got time, we're doing good. We're doing good. Okay, so make sure that these are equally spaced. So 360 degrees divided by 3 is 120 degrees, or 2 pi radians divided by 3 gives you that. You recognize you have a rose curve and find the first petal, just count over that many to get the tips and then connect the dots. So you really only need 3 dots. You don't need all this crap. So let's see if we can quickly graph. R is equal to I don't know. This time let's put the 3 out here, but let's put the sine of 2 theta here. Multiple angle is going to generate the petals. What's the 3 going to do?
It's gonna make it longer and
Make it
shorter.
longer. It's going to tell you how long R is going to be. So instead of R being 1, R is now going to be 3. Okay, this giveaway tells me that there's going to be 2 times 2 or 4 petals. The petals will occur at the angle measurements in which the sine itself hits 1 or -1. So what goes under my hand so that when I take the sine of that angle, I get a 1 or a -1?
Pi over 2.
Pi over 2s, right? So I need my 2 theta to be my pi over 2s, which means they occur at the pi over 4s. Okay, so the important points, the peaks of my petals are where 2 theta is pi over 2, 3 pi over 2, and so on. Or where theta is pi over 4s. That's where I hit the tips of my petals. That's where the sine of that is going to be 1. Where does the petals close?
At the. They're gonna close at the pies, which when you put it in the pi over 2 on our graph.
Okay, so where 2 theta is going to be 0, or where 2 theta is going to be pi, etc. Right? So that's theta is 0 and theta is pi halves. So if we're going to have 4 petals and the first tip occurs when theta is pi halves and closes at, when theta is pi fourths and closes at 0 and pi halves, doesn't that mean that your first petal is smack dab along the line y is equal to x? And then your second petal, let's figure it out. Let's just go. Come on, up here. Angelic music as I erase.
Courtesy of senior scam liker.
Yes.
I think I got like 15 from Pinehurst, Texas in like 2 days.
Yeah.
I blocked them.
At that point, I just answer and waste their time because they've been wasting mine.
There's my pi's over 4. Along the line y is equal to x and y is equal to -x. Okay, so here's what I'm plotting. We're just going to kind of plot it in our head. 0 pi over 4, pi over 2, 3 pi over 4, I've run out of room, so that might be enough. So I'm skipping the column for the two thetas. We're gonna do that part in our head. We're gonna double those angles, take the sine of them, and multiply them by 3. So beginning with 0, 2 times 0, 0, sine of 0, 0, 0 times 3 is 0. So next I'm putting pi over 4 in for theta. Double that, I get pi halves. Sine of pi halves is 1. 3 times 1 gives me 3. There's the tip of my pedal. Next one, put pi halves in here. Double it gives me pi. Sine of pi is 0. Pedal closes. So it went from 0 to 3 back to 0. Where do you think it's going to go next?
3.
From here,
-3.
it's going to go down here, right? It's going to go down to,
Or I guess it's just.
okay, so 3 pi over 4 in here. 2 times 3 pi over 4 is 3 pi halves. What's the sign of 3 pi halves?
-1.
So this becomes a -3. So here's 3 pi over 4. I have to go down here to -3. So the movement is there. Then it's going to close. Where's it going next?
The third quadrant.
Third quadrant. Then it's going to finish off up here. So it does it in a nice, smooth, continuous, like time pattern. We went up, down, down, up. Okay, but there's our 4 equally spaced pedals. 2 pi divided by 4. Those are all pi over 2 or 90 degrees apart. Okay, but notice how sine is symmetric to the y-axis. Cosine is always symmetric to x and has its first shape on the x. So multiple angles will do that. If I had a sine of 8 theta, I got 16 pedals. The tip of each pedal is going to occur 2 pi over 16 or pi eighths away from each other. So every pi eighths is going to be a tip of a pedal until I get all 16 of them. Okay? Okay, now, the next kind of graph gets rid of the negatives. And the way we can get rid of a negative is if I squared the R. And that eliminates the pedals that project in the opposite quadrants. So those things are going to look like this if you've got a cosine, or some version of a 45-degree angle version of that if you have a sine. And they'll have an R squared. And it knocks off the even pedals. So these will look like R squared is equal to A cosine of 2 theta, or R squared is equal to A sine of 2 theta. It's a multiple angle, but squaring it gets rid of those negatives, so it cuts off. Your book, I actually make the number in front a perfect square to make this pretty, so it makes an A squared here. Well, it doesn't have to be, like if I had a 3 there, you could think of that as square root of 3 squared. But that cuts off the negative pedals and just leaves you the positive pedals of a 4-pedal row.
Some of these graphs equal infinity.
They're infinity graphs, that's right. But they're called, I forgot what they're called. I call them 2-pedal roses, but that's not what they're called. The infinity symbols are called lemniscate. Two-pedal rows, none of the negative plotting to get the even things. So those are the important ones that we see over and over and over. And they are on page 451 of your textbook if you want to look those over. So see page 451. I think I also have some of the basic graphs on Blackboard, where I downloaded them from a page on the web. So if you learn the basic forms, then we can do the fun stuff with them, not just graph them. I mean, what's the point of a graph?
Show us what's going on.
we can find the area inside.
Oh, no.
Also,
Oh, no.
if we were gonna measure this length around, we can find those little parameters called arc lengths around the curve.
25 minutes.
In 25 minutes, we can find the area.
So what's the point of these graphs? Like, what do they show us, like in the real world?
In the real world. Now we're going in the real world from this classroom? Okay, so let's see, where does this occur? Not everything is polygonal. Some things are round. And so if things are nice and nearly polygonal, our idea is to cut things into rectangles and add the areas of rectangles. All right, now when you get a pizza, more than likely it's not cut into rectangles because then somebody's getting a little crappy piece that has more crust than anything else. And then somebody doesn't get any crust at all. How do they cut a pizza? From the center, right? Little triangular sectors of a circle. So what we're going to use these for is not to order a pizza, is to employ our chopping things up into little pieces and adding the areas of little pieces. But our little pieces now are going to be in sectors of circles.
And getting a pizza would be the best way to visualize.
But you guys probably want like weird things on your pizzas, pineapples.
Pineapple.
I was just gonna say
Little fishy
pepperoni.
things.
Pineapple is the best pizza.
Without.
There's a. I understand science. I want you to know how to.
My real world is the world of calculus. So I'm going to show you how our ideas in our rectangular plane can be translated to a polar plane. Well, the polar plane is often used in, for instance, physics. Why is that? Where do you use that in physics? Magnetism, right? Magnetism from a point radiates from a central point. So now I'm in electrical engineering because electricity moves in waves instead of along a straight line from a central source, right? So we've got to employ our ideas from our basic two-dimensional calculus so that we can get it in the polar plane. Once we get it in the polar plane, we can do things in space. Okay, so somewhat related to the real world. Somewhat.
Are we gonna start rotating these around an axis as well?
Not in this class.
Okay, thank you.
Right, but it is possible. So our question is, what if my cardioid is diagonal instead of sideways or up and down? Well, that just involves a change in coordinates. Okay, well, a change in coordinates, that's an algebraic manipulation. But you can do it with something called, you can do it with matrix arithmetic. You'll do a little bit of change of coordinates in your Cal 3 way at the end of the semester.
Will this?
I was just curious, when are we gonna do math with matrices? Like in
You'll see a
Cal
little
3?
bit in Cal 3,
Okay,
but yeah, just real little bit,
okay.
determinants and stuff like that.
I was wondering, can this be applied to like chemistry and calculating the areas of electron domains and molecules?
Why would you need to know that?
Well, I thought it was cool because if you can
looks
rotate
like
like
the
the
pedal
shapes,
works. Yeah, I
then
like
you
that,
could
yeah,
find
that's
the
like
areas of electrons.
If you
That's pretty
rotate
cool.
it, it's
I'm
just
gonna say
be like-
yes.
It doesn't.
Okay.
It's not as bad because it's just symmetrical and it just overlaps.
I try to forget all these things right now.
I was a chemistry minor, and I know nothing about chemistry, other than every question starting with methane, synthesize this.
So what you're saying is we don't have to know anything about anything to get a minor in something.
A minor is
No
hazing,
minor amount.
right? I had to have a minor, and I was a junior, and I had to declare a minor, and I needed something that was in the morning because I had a job in the afternoon. Then I needed something that I could do in the summer because I was a junior and I hadn't declared my minor yet. And so I did chemistry because in a summer, I did 1 year of organic chemistry. It was I still wake up going boo.
So like,
And you had to do labs, which took all day long. And I titrate, drip,
Oh my God.
drip.
Oh,
And you're supposed to see the results and, well, there was some sort of formula and then somebody doing the dripping. My dripping guy was Jim Bob Childress. Jim Bob was good at this lab stuff. I was good at the formula stuff. We were lab partners. So anytime we had to set up an apparatus or something, I said, be back in a minute. You get it set up, Jim Bob. And I would just start scribbling, make my table and kind of faking the data. And Jim Bob is over there just titrating his little heart out. He's having a real time. Middle of the summer, Jim Bob gets mono. Gone. I have no idea how to set up the little drippy thing. I gotta do it myself. So I would just kind of. Magic. It was chemistry magic.
Well, yeah, you were just doing alchemy.
It was. And if it was terrible. To this day, when I see Jim Bob, I,
How dare you get
how
mono?
dare you get mono?
Just roll. Do the same thing with.
Yeah. Watch you kiss.
Okay. What is the area of that circle? No two, just a pi. You know that the area of a circle is pi r squared. What if I just want a piece of a circle? Suppose I want this slice of the circle and I know this angle here.
Well, is it in
Is
radians?
R theta?
It's in radians.
Okay, so then you divide your answer by,
Pi squared by however big that is.
However big that is, what proportion that angle is to the entire circle. How many radians in an entire circle?
Pi.
So I would take that, so the area of a sector,
Is this a new,
this is still part of this section, but we're gonna look at finding areas of those bad boys. So we're gonna cut things up into sectors, so I need to know the area of a sector. So it's the area of a circle multiplied by part over the whole. Part over the whole times pi r squared is the area of a sector of a circle. Well, that simplifies. I can get rid of the pi's. So that's going to be theta over 2 times r squared. That's the area of a sector. Okay, so here's our idea. We've got a curve in polar coordinates. Here's just a random, r is some function of theta. I want to find the area in the curve, say from theta is equal to A up to theta is equal to B. So I want to find the area of this blob right in there. So I'm going to make an infinite number of cuts in this thing with rays from the origin. So I'm going to partition the region into infinitely thin rays from the origin. And so let's just look at, say, the kth partition. Okay, so I'm going to partition the region into an infinite number, let's just say n sectors, each of angle delta theta. So the angle here is a change in theta, right? In the rectangular coordinates, we cut up the x-axis with widths of rectangle of delta x. Theta is going to be my independent variable. I'm going to cut my sectors into angles of width of delta theta. And they're so small that if you look at that sector, you don't see this concavity portion. It looks like a sector of a circle. So the area of one of, and they're so small that this R is essentially the same length as that R. The kth sector has a radius on the average of R with a kth subscript. So the area of the kth sector is going to be whatever the average radius is squared, divided by 2, and then multiplied by the angle measure, which we said was going to be a delta theta. So I've got a whole bunch of them. I'm going to add these up from k is equal to 1 to n, and then I'm going to let n go to infinity. So I add them up with a Riemann sum. Okay. The sum from k is equal to 1 to n of pieces that look like that. And I'm trying to keep my delta thetas all about the same size. Then I'm going to take the limit of that as n goes to infinity. What happens when you take the limit as n goes to infinity? It becomes an integral. It becomes an integral. We get an integral. The theta is the independent variable. I'm going to have a factor of a half here. And then I've got my r squared. Well, what was r? R is whatever that equation is, one of our shapes. R is cosine theta. R is 2 plus 2 cosine theta, whatever the function is. And so in here, we'll put the function's formula as a function of the independent variable theta, but you got to square it. And then this goes from theta is equal to A to theta is equal to B. So in polar coordinates, there's the formula for area. It's not base times height. It comes from the area of a sector of a circle. Now, think of those equations that we had up here. They had sines and cosines in them. So somewhere down the line, we're going to square them and get a sine squared or a cosine squared, and we have to know how to integrate that. The integral of sine I know, the integral of cosine I know. Unfortunately, the integral of sine squared is not the integral of sine itself squared. We've got to figure out how to integrate sine squareds and cosine squareds before we can apply this formula to our brand new polar curves.
New substitution.
Almost. Who knows their trig?
Is it?
Oh,
chain
wait,
rule?
sine
We have
squared
a trig power reduction formula for sine squared. And I saw sine squared is 1 minus cosine squared. Cosine squared is 1 minus sine squared. That doesn't help me because it keeps a second degree power.
Sounds familiar, but I don't remember what it is.
I was hoping you remembered because now I'm stumped.
Sorry.
That's a lie. I'm not stumped. I teach trig on Tuesdays and Thursdays to my COVID carriers. How about, do you know the half angle formulas?
I don't know.
We talked about it one time, but
Yeah, I forgot this because I said I'm never going to use this again. And
Until
right now,
September, what, 1st?
yeah,
Yes, ma'am.
2021.
All right, so you used it probably in 1990 something.
Yeah.
And now here it is, September 1st of whatever year this is, 21. All right, the sine of half an angle and the cosine of half an angle look almost identical in terms of the sine of the angle. They both have a square root. They both have an over 2. And they both have 1 and a cosine of theta. The sine has a minus, cosine has a plus. Now I'm going to square both sides to get rid of the square root sign. Okay? So I'm going to square this side. I'm going to square that side and use my towel to get rid of the square root sign. You guys can just write this underneath. Oops, these should have A's in them, sorry. Those are A's.
Okay.
Yeah. Whatever the angle is halved here is the whole version of it here. So there's a square. And now I'm going to replace each A with 2 times theta. Replace each A with 2 times theta, and I have my power reduction formulas.
Why? Oh, because you're canceling out that too.
So if I put, if A is 2 theta, 2 theta divided by 2 just gives me theta. That's the guy I'm trying to integrate. So I'm going to replace this A with 2 theta. So if I want to integrate this, I integrate that instead. That's a first degree cosine. I can integrate that. That's a constant. I can integrate that. If I want to integrate, I'm replacing A with 2 theta. Replace A with 2 theta. I'm almost integrating the same thing each time. The integral of the sine squared and the integral of the cosine squared is going to look very similar to each other, just off by that constant in the middle, that plus or minus. So let's go ahead and integrate the sine squared. Integrated sine squared, I replace sine squared with the expression 1 minus cosine of twice the angle over 2 times d theta. I'm going to pull out the 1/2 way out front and then integrate term by term. We'll do this part. Integral of 1 with respect to theta is theta. Okay, this is a double angle. So if u here is 2 theta, then du is 2 times d theta, or d theta is 1/2 of du. So I would integrate 1/2 cosine of u du. This is what I just did in my head.
And also,
So the du over 2 cosine of u is that. So now you're going to integrate that as a function of u. What's the integral of the cosine of u?
Negative sign.
Negative or positive? Positive sine of u. But u was 2 theta. So here I'm going to get 1/2 sine of 2 theta. So I get 1/2 sine of 2 theta plus the constant of integration. I'm going to distribute the 1/2 now and write this like this. Theta over 2 minus the sine of 2 theta over 4. And that's going to be the integral plus c of sine squared of theta. What's going to be different when you integrate the cosine squared?
it will be a plus.
We'll have a plus in between the two, right? We're going to use these so many times, it'll help if you just memorize these as formulas. Why reinvent the wheel each time? And I always memorize it this way, theta over 2 plus sine 2 theta over 4. Add this to the list of definite integrals that you now know. If you forget it, you can just whip out the old identity. But you don't have to each time if you can just make that jump. What I want to do next is show you that this formula works for one of our easiest shapes, one of those circles that have been shifted on the X or Y axis. Because we know by geometry what their area is going to be. I'm going to show you that the formula works on that, and then that'll probably be all the time we have. So let's go and take a circle. R is equal to 6 sine of theta. R is equal to 6 sine of theta was the second one I dropped. That was the circle with the diameter of 6, symmetric to the y-axis. Let's use this formula to find its area. So, example. Find the area enclosed by R is equal to 6 sine of theta. We graphed it earlier. It's the circle up here. Radius is 3. Diameter is equal to 6. Without using calculus, what is the area of a circle of radius 3?
9 pi.
9 pi, pi r squared. So we know before we start, our answer using this formula is 9 pi. Okay? But now let's use our formula because that's why we have it. Let's try a bit of calculus. So this is my f of theta, 6 sine theta. So I have to integrate 1/2 6 sine theta all squared d theta. Then I look at the picture. What are my angle measurements going to be if I slice that up from theta is equal to what to what?
0 to 2 pi.
Not to 2 pi, look at my picture. It's all above the x-axis. It's from 0 to pi that my rays will slice that up. So I'm going to integrate from 0 to pi 1/2 6 sine theta all squared d theta,
So
right? From 0 back to pi, cuts that up into little sectors.
you wouldn't move it down or anything like that?
How would I want to move it down?
That way the center is on the center. And you have pizza slices.
Well, I guess you could, but then it didn't no fun using the formula. Right? Constant squared, boring. What's the point of this? Okay, so using area is equal, don't ever forget the 1/2. F of theta squared d theta. We are going to have our area is 1/2 integral. So again, 0 to pi generates the whole figure. And then I have my 6 sine of theta in here. Got to square it first and then integrate it. So don't forget to square the 6. 6 squared will give me 36. I'm going to take the 36 out front with the 1/2. 1/2 of 36 is 18. So I'm going to have an 18 out here. Now my sine squared to be integrated here. In my box, I see the integral of sine squared is theta over 2 minus sine of 2 theta over 4. Theta over 2 minus the sine of 2 theta over 4. And I've got to evaluate that from 0 to pi. Okay. Look at that second term there, 2 theta. I'm going to substitute pi for theta and 0 for theta. So I'm going to compute the sine of 2 pi and the sine of 0. I know those numbers. Those are both going to be 0. So this term doesn't even provide me anything other than 0. This term is going to give me a pi over 2 minus 0. So I'm going to get pi over 2. So I have 18 times pi over 2. 18 times pi over 2 is 9 pi. Kind of comforting that it works for something that we know. Because now I believe it's going to work for our cardioids and our rose curves and things like that. Cardioids are going to be easy to find the area of because look at our cardioids. They're centered. It took a whole lap around the circle to graph one of those cardioids. So cardioids will always integral from 0 to 2 pi. Now, when you have a rose curve, it didn't take us a whole 0 to 2 pi to graph that thing. Because remember, the period's condensed. So what I'm going to do to graph the rose curve is find out where one petal is, where it opens and closes, find the area of one petal, and then multiply by the number of petals. Okay? Because if you integrate 0 to 2 pi on a rose curve, you're going to go around that rose curve several times. You're going to get too much area. So practice some of those problems, and then next time we'll do some more examples, and then we'll talk about arc length and rectangular coordinates, and arc length and polar coordinates. This is still section 6.3.